All right, in this video, I want to do one more expected value problem where we're going to interpret this as a game and like a profit or losses problem. And so this is a lottery problem. And I've just constructed a basic, kind of like a baby lottery. Most lotteries are more complicated than this. I'll talk about some complications at the end. But the idea here is that what we're going to do is we're going to pay $5 to play this lottery game. And then the game is going to consist of 6 numbers being randomly selected from 1 to 50. This is 6 numbers without replacement. And if we get all 6 correct, we're going to win $30 million. So we'll earn a profit of $30 million. And otherwise we just lose our $5 that we played with. And so the idea is it a good idea, mathematically speaking, to play this game? And so what we have to do is we have to find the expected value, figure out whether it's positive or negative, and that'll tell us our answer. And so what we need to do is think about a random variable. Let's let x count our winnings, just like in the previous example. So let x count our winnings. And then there's going to be 2 options that can happen. There's 2 scenarios. The first is we can either lose $5. Okay, not surprising. The second option is that we can win $30 million minus the $5 that we had to pay to play. So actually it's just a net profit of $29,999,995. And then we need to think about what's the probability that each of these events occur. And so let's think about what's the probability that we win. Well, this is gonna bring us back to our counting section where we talked about we have to pick the correct set of 6 out of 50 numbers. And this is a combinatorics question. This is a combinations question. So of the 50 numbers, let's think about how many lottery tickets there are. Of the 50 numbers, we want to choose 6 of them. And there's only 1 winning lottery ticket. So it turns out that the probability that we'll win is 1 divided by 50 choose 6. And I'm going to use R to calculate what this is. So actually, let me just show you my entire desktop so we can bounce back and forth here. Okay, so we have 50 choose 6. And so that's 15 million, more or less. So this is 1 out of 15 million. Let's go back to the iPad. So this is 1 out of 15 million, oops, 890,700. So that's our chance of winning. And our chance of losing is 1 minus that. 1 minus 1 over 15,890,700. And then we're asked to find the expected value. And the expected value is going to be minus 5 times 1 minus so minus 5 times the corresponding probability. So that's 1 minus 1 over 15,890,700. We're going to add to that this value, this 30 million minus 5, times the corresponding probability. So that's going to be 29,999,995 times 1 over 15,890,700. And so the moment of truth here, we need to plug everything in. And when we plug everything in, let's think about what will happen here. So we're going to take negative 5 times 1 minus 1 over 15,890,000 plus 29,999,995 times 1 over 15 million. And it turns out when we plug it in, what's going to happen is we're going to get, let R go to work here, we're going to get negative 3.112, let's say $3.11, negative $3.11. And so on average, What this means is that we're going to have an average loss of $3.11 every time. If we play this game a million times, statistically speaking, we will have probably lost $311 million. So it's a bad idea to play it a million times. It's a bad idea to play it once. Of course, there's complicating factors to this problem as well. So if you win a lottery of $30 million, your take-home money is like $12, right? You get taxes taken out of it. It's not really $30 million that you win. That has to be accounted for. That's a negative. One complicating factor on a positive is that a lot of them have sub prizes, so that if you get 5 of the 50 numbers, you get a certain amount of money. If you get 4 out of the 50 numbers, you get a certain amount, and so on. So again, some complicating factors here, but in general, lotteries are a bad idea, mathematically speaking.